The ideas of Bose and Einstein have had a decided impact, and they come into play in commonplace settings. Everyone today is familiar with the laser pointer, the green laser pointer which is used for presentations, but also is on evidence in, for example, soccer matches where less reputable members of the audience point lights at players on the field to distract them. Here's a very commonplace idea, the idea of a laser. The existence of lasing abilities is due to the fact that photons follow Bose-Einstein statistics. They are identical particles which are non-interacting, and many of them can land coherently in the same bin and form, for example, a coherent beam of light, a laser. One also finds this at play in more exotic circumstances. For example, Bose-Einstein condensates have a particular and potent role to play in this phenomenon called superfluidity, and also in superconductivity. Though, of course, in the interest of full disclosure, the ideas have to be adapted, because in those settings, the particles actually do interact, and so one needs to massage the basic understanding here. But with all these successes, as early as 1926, it was clear that we still had difficulties explaining things at the level of electronic fluctuations. For example, the Bose-Einstein statistics don't explain why the specific heat of electrons in a metal at room temperature is what it is. The classical theory predicts that one should need a lot fewer electrons in the current for the observed specific heat than one actually gets. This is strange. And of course, when one gets data that are not in consonance with the theory, that suggests that one has to revisit the theory. The same kind of puzzling phenomenon arises when one looks at emission currents at room temperature. And again, there are gaps between what the theory says and what we actually observe in practice. In 1926, a couple of years after Bose and Einstein published their paper, Enrico Fermi and Paul Dirac, two more giants of 20th century physics, proposed a new model to handle things like electronic fluctuation. Fermi is famous through, for example, the Fermi labs, which now sadly is defunct. Paul Dirac was a brilliant British physicist and mathematician. They wanted to explain these phenomena, things like, why do electrons apparently not subscribe to the Bose-Einstein model? And so they needed a key insight. Now, what was their key insight? Again, the setting is, we have a random placement of n balls into R urns. The balls, of course, are your particles, whatever flavor they are. The urns represent physical states of being of these particles. Following the insight of Bose and Einstein, Fermi and Dirac say, well, we are going to consider these particles as if they were indistinguishable balls. But we need something more. And this is what they happened upon. What if the balls were exclusive, snobbish? What if each ball refused to share an urn with a neighbor? In other words, we are constrained to have occupancies which could only be 0 or 1. No urn's occupancy could be 2 or more. This principle, that urns could be at most singly occupied, is called the Pauli exclusion principle, named after Wolfgang Pauli. So now we have a new model. We have indistinguishable balls, R urns, and the additional Pauli exclusion principle as a constraint. No urn can contain more than one ball. Think of this as a very exclusive neighborhood. Each ball wants its own house, and it wants nobody else living with it. Now, some things are immediately clear. If each ball has its own urn, then the number of balls cannot exceed the number of urns. In theoretical computer science, this is sometimes called the pigeonhole principle. You have a certain number of pigeons, the balls, a certain number of holes, the urns, and if every pigeon is to get its own hole, then the number of pigeons cannot exceed the number of holes. Okay, so immediately we know that n cannot exceed r. In addition, we know that occupancy configurations here, K1, K2 through Kr, are strings of zeros and ones only, because no occupancy number can exceed 1. It can only be a 0 or a 1. Of course, then we conclude that the K1 through Krs are either 0 and 1, and they must, of course, add up to n. All the balls are accounted for somewhere in the urn system. Now, let's take a look at a picture. And again, following Pauli's sage advice, let's look at a simple model. 2 indistinguishable balls, 4 urns. How can we distribute them in accordance with Pauli's exclusion principle? Well, here's an example. Let's say urn 2 and urn 4 contain 1 ball apiece. This, of course, gives you an occupancy configuration, 0, 1, 0, 1. Now, let's stare at this picture for a little bit. A generic picture is going to look like this. Now, what does that mean? It means that there are R locations, in this case 4 locations, 4 urns, and the moment you specify a ball has gone into an urn, then that urn cannot be reused. In other words, the placement of balls into urns is a selection methodology which selects which urns are occupied. In this case, of course, there are exactly 4 choose 2 ways of specifying the 2 occupied urns, and of course this is 6. And of course we immediately generalize. If we have a setting where you have n indistinguishable balls, R urns, balls are distributed into the urns in such a way that no urn contains more than 1 ball, then this is equivalent to specifying which n of the R urns are occupied. And of course, there are exactly R choose n ways of doing this. Now we've come to a right understanding of what the Pauli exclusion principle constrains us. We only have R choose n distinguishable configurations, distinguishable occupancy numbers. Now, once you have these, again, there is no a priori reason to believe that one particular configuration is any more likely than other. And therefore, we assume that all these configurations are equally likely. Now, what then is a chance of one particular occupancy configuration arising? Well, it is the reciprocal of this number. And so we now have the Fermi-Dirac statistics. The probability that if n indistinguishable particles are launched into R urns while satisfying the Pauli exclusion principle, the probability of observing one particular occupancy configuration is the reciprocal of R choose n. Bear in mind that the occupancy configurations we are talking about here, right, must correspond to occupancies which are either 0 or 1, and of course the sum must be exactly n. All the particles must be accounted for. Okay, this is all well and good, but of course the true test of such a theory is whether it is validated in practice. And one finds in the 20th century a triumphant vindication of this idea. A whole class of particles called Fermions, in honor of Enrico Fermi, fall into this bin. From a physicist's point of view, these are particles which have 1/2 of an integer in spin. They have half integer spins. Examples are electrons, protons, neutrons. These are all elementary particles. An electron, for example, is a spin 1/2 particle. And all of these have been shown to follow these statistics. More complex particles also fall into this bin. For example, the helium-3 atom or the carbon-13 atom. This then gives us a satisfactory picture of a separate class of particles. Of course, one understands that these are elementary models, and while they illuminate the big picture, there is much more there. Okay. And of course, to understand the real statistical physics, one has to figure out how these particles interact with each other, how the bosons flow to the fermions and vice versa. Of course, then this gives us the rich edifice, which is the modern-day statistical theory of the atom. Yeah. But for our purposes, already these elementary ideas, and this is the take-away message, simple ball and earn models, variations on that theme, already elucidate, illuminate key fundamental principles of modern physics.